Welcome back, friends. Currently we are dealing Euler's critical load. We are trying to derive a formula for Euler's critical load. We derived it in last session. We are discussing various points on this Euler's critical load. So in previous session I talked about mode number, mode shape number, number of stops, relation between mode number and number of stop, etc., etc. So in GATE exam, what kind of questions are coming on this topic? The question came like this, man. A column is buckled like this. Both ends are pin jointed, man, right? A column is buckled like this. Euler's critical load of this column is 1000 newtons. What is Euler's critical load of this column? So originally column is buckling like this. Euler's critical load of this column is 1000 newtons, man. If same column buckles like this, what is Euler's critical load? Maybe this is first column, this is second column. Euler's critical load of second column by Euler's critical load of first column is equal to dash. So this question came in GATE. The formula is P is equal to n square pi square EI by L square. For first column, what is n? 1. So critical load is pi square EI by L square. What is mode number for second column? Okay, I am writing here, man. For this column n is equal to 1. For this column n is equal to 2. What is critical load of second column? 4 pi square EI by L square. What is critical load of first column? Only pi square EI by L square. When n is equal to 2, 2 square 4. When n is equal to 1, 1 square 1. So what is the answer, man? 4. The Euler's critical load of second column by Euler's critical load of first column is 4. So this question already came. In coming GATE exam, they may try like this. A column is buckling like this. A column is buckling like this. Maybe this is third column. Mode number is 3. Mode number is 3. What is P3 by P1? Euler's critical load of this column by Euler's critical load of this column 9 times. What is P3 by P2? Euler's critical load of third column by Euler's critical load of second column. How many times, man? P3 is 9 pi square EI by L square. P2 is 4 pi square EI by L square. That means P3 by P2 is equal to 9 by 4. 9 by 4. Like this, they may give a comparison problem. They may give two columns with different modes and they may try to compare the critical load of the columns. So be ready for it, right? So like this questions may come. Please copy. First copy this. This is 1. This is 2. This is 3. First, what is P2 by P1? 4. What is P3 by P1? 9. What is P3 by P2? 9 by 4. Please do all these things, man. That P2 by P1 question already came. In coming GATE exams, they may ask you what is P3 by P1 or P3 by P2. P3 by P1 or P3 by P2. Please copy. If critical load of this column is 1000, what is critical load of this column? And 4 times 4 times is 4000. So I should write somewhere here. So if P1 is equal to 1000 newtons, P2 will be 4000 newtons and P3 will be 9000 newtons, man, right? So you may add these 3 points also. If critical load of this column is 1000 newtons, what is critical load of this column? 4000. What is critical load of this column? 9000. Let us deal one more point. I hope you copied. Right. A general question, man, right? A general question. A general question. Critical load of this column is 1000 newtons. Critical load of this column is 1000 newtons. If same column is buckling in nth mode, what would be the critical load? If this column buckles in nth mode, what is critical load? First copy this. Critical load of this column is 1000 newtons. Critical load of this column is 1000 newtons. Now write down the sentence. If above column buckles in nth mode, if above column buckles in nth mode, critical load becomes dash. Critical load becomes dash. Critical load becomes dash. So what is the answer, man? The answer is n square times of 1000 newtons. Critical load is always proportional to n square. So n square times of 1000 newtons. N square times of 1000 newtons. Okay? Right. Last question, man. How many critical loads will be there for a given column? How many critical loads? Only one critical load or infinite critical loads? The answer is infinite critical loads. The column carries not single critical load, man. It may carry infinite critical load. The critical load corresponding to column like this, if column buckles in first mode, the critical load corresponding to this column is called the fundamental critical load or first critical load. Fundamental critical load or first critical load. Second, the critical load corresponding to this is second critical load. The critical load corresponding to mode shape like this, third critical load, fourth critical load, fifth critical load, like that, man, right? With every mode shape, a critical load will be there. So number of critical loads for column is infinity. It is not one. Please write down. Number of critical loads for a column is infinity. Number of critical loads for a column is infinity. And next point. The critical load of column corresponding to first mode is called fundamental critical load, or first critical load, or basic critical load, basic critical load. Okay? One more question is coming to my mind, man, right? Euler's critical load P is equal to n square pi square EI by L square. One more gate question is coming to my mind. A cylindrical column is there. Diameter of column is D. If diameter is double, okay, if diameter is double, what will happen to Euler's critical load? This question came in gate. When diameter is double, what will happen to Euler's critical load? So Euler's critical load is proportional to I, right? P is proportional to I. But what is moment of inertia of cylindrical column? I is equal to pi by 64 into d power 4. So moment of inertia of cylindrical column is proportional to d power 4. That means here I can write P is proportional to d power 4. Euler's critical load is proportional to d power 4. If d is doubled, what will happen to P? If d is doubled, what will happen to P? 2 into 2 into 2 into 2, 4, 2 into 2, 4, 4 into 2, 8, 8 into 16, 16 times. When diameter of this column is doubled, Euler's critical load becomes 16 times of original critical load. 16 times of original critical load. Okay, this kind of question also came. And in another gate exam, a rectangular column is there. A rectangular column. In the rectangular column, all dimensions are doubled. A rectangular column is there like this, right? So this is B and this is D. Obviously, you know what is moment of inertia. Moment of inertia is BD cube by 12 if B is more than D. So always in columns, moment of inertia means lowest moment of inertia, least moment of inertia. If B is more than D, obviously this is moment of inertia, right? This is original moment of inertia. When all dimensions are double, what will happen to I? B is double, D also double. So what will happen to moment of inertia? Moment of inertia becomes 16 times of original moment of inertia. Obviously, Euler's critical load also will become 16 times. When moment of inertia changes, critical load will change. More moment of inertia means more critical load. Like that you have to understand. Okay? So this kind of questions also coming. If you know this formula, you can easily do all these kinds of problems, right? The trick is here knowing formula. If you know formula, you can do all the questions on this formula, right? Okay. Okay. We derived formula for Euler's critical load, but still I don't know what is C2. In our derivation, we found C1 is equal to 0. C2 we don't know, man. Still we don't know what is C2. Let us try to find C2. So I'm going back to my derivation. Y is equal to C2 into sin kx. Y is equal to C2 into sin kx. Still I don't know what is C2. I don't know what is C2. We have to find what is C2. To find C2, I may use another boundary condition. At x is equal to L by 2, y is equal to delta. X is equal to L by 2 means midpoint. At midpoint, what is displacement? Delta. Okay? At x is equal to L by 2, y is equal to delta. So I am putting this boundary condition. I should say delta is equal to C2 into sin k into L by 2. K into L by 2. What is K? We know what is K. K is equal to n pi by L. K is equal to n pi by L. And if column buckles like this, what is n man? Is it first mode or second mode or third mode? It is first mode. So for first mode, K will be equal to pi by L. For first mode, n is equal to 1, K becomes pi by L. Then upon putting this, delta is equal to C2 into sin pi by L into L by 2. Delta is equal to C2 into sin pi by L into L by 2. LL will be cancelled. We are getting pi by 2 here. What is sin pi by 2? 1. 1 into C2, C2. C2 is equal to delta. So we just found what is C2. C2 is equal to delta. Then my solution will be y is equal to delta sin pi x by L. So this is the solution, man. For first mode, K is equal to pi by L. Right? In this expression, in place of K, I am writing pi by L. In place of C2, I am putting delta. So this is our solution, man. And I should say, this is only valid for first mode. This is only valid for first mode, man, right? So y is equal to delta sine pi x by L. Please copy all these contents. I hope you copied. So what this formula is saying, how this column is buckling, how this column is buckling. This formula explains you how column is buckling. Column is buckling in the shape of circular arc, elliptical arc, parabolic arc, hyperbolic arc, or sine wave. This formula is saying this column is buckling in the form of sine wave. Because sine is there here, right? It is buckling in the form of sine wave. You know, sine wave, cos wave, tan wave, like that, man, right? Write down. Write down this point. The above expression shows. The above expression shows. The above expression shows. The column buckles. The above expression shows. The column buckles in the form of sine wave. The column buckles. The column buckles in the form of sine wave. In the form of sine wave. Sine wave. S-I-N-E, sine wave. Okay? Right. We're going to do some problems on this formula also, but not now. First, let me finish the concept, then we do some numericals on columns, right? Some numericals on columns, okay? Right. So we derived Euler's critical load when column is pin jointed on both ends. Let us try to deal remaining end conditions also, right? Remaining end conditions also. I am not going to derive every formula, just I am giving directly the formula. And if you want to learn derivation of every end condition, you can refer any standard textbook, including reference books which are given at the beginning of SOM. I have given some reference books at the beginning of SOM. You can refer them, right? All those things are given. So second case, in second case, a column is fixed on both ends. Column is fixed on both ends. Okay, column is fixed on, you write like this. Column with both ends fixed. Column with both ends fixed. Column with both ends fixed. In GATE exam, they can use all these terms, man. Fixed. It is same as flanked. It is same as clamped. It is same as Bolton. It is same as encastered. It is same as bolted. It is same as riveted. It is same as welded. You know, instead of fixed, they can use any of these terms, man. They can use any of these terms. Always they need not use fixed. They have already used flank in one gate exam. In another gate exam, they used clamp. In another gate exam, they used Bolton. So always they need not use term fixed. They can use any of these terms, man. Please copy. Fixed is same as all these words. Please copy. I hope you copied. What is critical load of this column, man? Both ends are fixed. Most of the columns are fixed. Most of the columns are fixed columns, man. Especially concrete columns, they are fixed. Okay? So the critical load of this column is 4 pi square EI by L square. It is for first mode, and P is equal to N square 4 pi square EI by L square in nth mode if N is very much bigger than 1. So this is point, man, right? When N is more than 1, very much bigger than 1, approximately we can find critical load by using this formula, N square into 4 pi square, or in this fashion, right, man, right? Then you will understand easily. You may write in this fashion, N square pi square EI by L square, multiply this with 4, right? Then you will understand. Okay? Please copy these two. In first mode 4 pi square EI by L square. In nth mode 4 into N square pi square EI by L square when N is very much bigger than 1. Right. Let's move to another case, man, right? Another case of N conditions. You may write third case, man. Third case. One end is fixed, other end is pin jointed. You may write in this fashion, man. One end is fixed. One end is fixed. Other end is pin jointed. Bottom is fixed. Other end is pin jointed. One end fixed. Other end is pin jointed. Other end is pin jointed. Pin jointed. Okay. The critical load of this column is 2 pi square EI by L square. This is in first mode. And this is equal to 2 into N square pi square EI by L square in nth mode. Here N is very much bigger than 1. So copy these two. The Euler's critical load of this column in first mode is 2 pi square EI by L square. Euler's critical load of same column in nth mode is 2n square pi square A by L square. 2n square pi square A by L square. So please copy. I hope you copied. This is for first mode. This is for nth mode. Okay. Let's move to next case, man, right? Next case. Fourth case. You write like this. One end fixed, other end is free. One end fixed, one end is fixed. One end is fixed, other end is free. One end is fixed, other end is free. Like this, man. Try to think about some examples of this case. This is another general case. Both ends fixed, one end fixed, other end is free. These two cases are very popular cases, man. Very popular cases. Try to explore some examples for this case. Try to think about a telephone pole. Try to think about an electrical pole. Try to think about chimney. Try to think about straight-tongued trees. Some palm trees are, some palm trees are very much straight. Some coconut trees are very much straight. All those straight-trunked trees can be imagined as this column. Okay? One end is fixed, other end is free. So what is critical load of this column? P is equal to pi square EI by 4L square. Pi square EI by 4L square. All these derivations are available in every standard textbook of SOM. Okay, every derivation we need not do in gate classes, right? We did basic derivation, it is more than enough. For remaining cases, just remember formula, that is more than enough, right? If you want to know how this formula is derived, you can refer any standard SOM textbook, right? So this is the formula to find Euler critical load when one end is fixed, other end is free. One end is fixed, other end is free. Okay, please copy. So here, generally critical load is defined only for first mode main rate. For nth mode, for higher modes, generally we don't define critical load. We can define, but generally we don't define. So P is equal to pi square EI by 4L square. Pi square EI by 4L square. So these are the basic end conditions, man. Few more end conditions I am going to discuss later. These are 4 standard end conditions for mechanical students. These 4 are enough. For civil students, few more I am going to cover. Understand, man? Always mechanical students are getting questions from only these 4 standard cases. Both ends pin jointed, both ends fixed, one end fixed, other end is pin jointed. Fourth, one end fixed, other end is free. Only from these 4 standard cases, mechanical students are getting questions, but civil students are getting questions from few other cases also, man. I am going to discuss those cases also, right? Right now, only 4. What kind of questions may come in gate exam on this topic? Standard question, man. A column is fixed on one end, free on other end. Critical load is equal to 1000 newtons, for example. A column is fixed on one end and free on other end. Critical load of this column is 1000 newtons. If other end is also fixed, what is critical load? If other end is also fixed, what is critical load? Maybe this is first column, this is second column, right? P1 is equal to 1000 newtons, what is P2? This is very standard question, man. Very standard question. Okay? If critical load of this column is 1000 newtons, what is critical load of this column? Very standard question. So, P2 by P1 is equal to, what is critical load of this column? 4 pi square EI by L square divided by, what is critical load of this column, man? Pi square EI by 4 L square. If they don't mention mode number, you have to assume mode number is 1. If you don't mention any mode number, just assume first mode number, first mode shape. So what is the answer, man? It is 16. After cancellation of all these things is 16. That means P2 is equal to 16 times of P1. The 16 times is very important, man. Very popular question. Right? Very popular question. So critical load of second column is 16 times of critical load of first column, or if other end is also fixed, critical load becomes 16 times of original critical load. Now what is P1 here? 1000. So that 16 into 1000, 16,000 newtons. 16,000 newtons. This is very popular question. Please copy. Okay. Same problem could be asked like this also, man, right? Critical load of a cantilever column is 1000 newtons. If it is fixed, what is critical load? Like that also they can ask. Cantilever column is like this, man. Cantilever column is similar to cantilever beam, meaning cantilever beam, one end will be fixed, other end will be free, is it not? Like that, in cantilever column, base will be fixed, other end will be free. This is called cantilever column, man. This is called cantilever column, and this column is called fixed column. And this column is called fixed column. So, critical load of the cantilever column is 1000 newtons. If it is fixed, what is critical load? What is answer, man? 16,000 newtons. Same to same. Okay? If cantilever column is converted into a fixed column, what will happen to critical load? Critical load will be incremented by how many times? 16 times. If a cantilever column is converted into a fixed column, critical load becomes 16 times of original critical load. 16 times of original critical load, right? So this is very popular question, man, right? Very popular question. Okay. This is cantilever column. Critical load is 1000 newtons, man. This cantilever column is converted into simple column. This is called simple column, man. If both ends are pin jointed, that column is called simple column. Simple column. Critical load of cantilever column is 1000 newtons. What is critical load of simple column? Maybe this is second, right? What is P2 by P1? What is P2 by P1? So P2 is pi square EI by L square. P1 is pi square EI by 4L square. That means how many times, man? 4 times. So critical load of simple column is 4 times of critical load of cantilever column. Critical load of simple column is 4 times of critical load of cantilever column. That means in this case, so P2 will be equal to 4 into 1000. How much, man? 4000 newtons. Critical load of this column is 4000 newtons. Please copy this also, man. I hope you copied. So we compared cantilever column, fixed column, we compared cantilever column and simple column. Like this, from this Euler critical load formula, regularly problems are coming in GATE exam. Be careful, right? Now we are going to start another important, topic in these columns, that is effective length. Effective length. Effective length or equivalent length. Effective length or equivalent length. Effective length or equivalent length. First I define, then we have a little discussion on what is effective length or equivalent length, right? Right definition. It is length of column. It is length of column which gives. It is length of column which gives same critical load. Same critical load. It is length of column which gives same critical load. Same critical load when column is pin jointed. When column is pin jointed. When column is pin jointed. So effective length is defined with respect to pin jointed column. So another definition I want to dictate. Another definition. It is length of half of the sine wave. It is length of half of the sine wave. It is length of half of the sine wave. Half of the sine wave. Okay. So what is sine wave? This is sine wave, man. For one cycle, this is 0 degrees. This is 90 degrees. This is 180 degrees. This is 270 degrees. And this is 360 degrees. 0 degrees sine value is 0. 180 is 0. At 90, positive maximum. 270, negative maximum. This is called sine wave. Full sine wave, man. That is half sine wave. Half sine wave. This is another half sine wave, man, right? This is another half sine wave. So what is effective length? It is length of half of the sine wave, man. For instance, a column is buckling like this. The actual length of column is L. What is effective length? What is the effective length? Actual length is L. What is effective length? What is effective length? Length of half of the sine wave. This is a half of sine wave. This is another half of sine wave. This is one half sine wave. This is second half sine wave. What is length of each half of sine wave? This is L by 2. And this is another L by 2. This is another L by 2. Okay. Then what is effective length? Effective length LE is equal to, it is length of half of the sine wave. It is nothing but L by 2. It is nothing but L by 2. Each length of half of the sine wave is effective length. Similarly, a column may buckle like this. A column may buckle like this. What is effective length? Total length of column is L. This is L by 3. This is another L by 3. This is another L by 3. So how many half sine waves are present in this problem? How many half sine waves are present in this problem? First half sine wave, second half sine wave, third half sine wave. 3 half sine waves are available. Length of each half sine wave is effective length. Then what is effective length here? Effective length LE is equal to L by 3. Length of each of the half of the sine wave is called effective length. Okay? Right. There is another definition, man, right? Another definition of effective length. You may write it. Another definition of effective length. It is distance between. It is distance between. It is distance between two consecutive inflection points. It is distance between two consecutive inflection points. Distance between two consecutive inflection points. Two consecutive inflection points. In beams, we call this inflection point as point of counterflexure. In columns, this point as inflection point. What is this inflection point or point of counterflexure? Let us take one example here. This is one inflection point. This is another inflection point, man. There are two inflection points. This is inflection point. This is another inflection point. What is inflection point? Above this point, column is bending towards right. Below, just below this point, column is bending towards left. So about inflection point, column is, or curvature of column is changing from positive to negative or negative to positive. Above, rightward bending is there, buckling is there. Below, leftward buckling is there. About inflection points, the column carry two opposite curvatures, man. Contra means opposite. Inflection also means opposite. Okay? So this is effective length, distance between any two consecutive inflection points. Any two consecutive inflection points. Okay? One more definition, man. One more definition. It is length of bow. It is length of bow. B-O-W, bow. You know, the bow is almost in the shape of sine wave. So that is why some scientists have defined like that, man, right? Length of bow. So in this column, how many bows are there? How many bows are there, man? First bow, second bow. Length of each bow is effective length. Length of each bow is effective length. Okay? So this is regarding effective length. In coming session, we are going to deal various kinds of end conditions. What is effective length? What is critical load? What is specialty of that? So all those things I try to cover in the form of table, man, right? End conditions, then critical load, then effective length, then effective length factor, like that. We try to deal, okay, various end conditions in the form of a table. But before the table, here I am writing a universal formula of critical load of column. Critical load of column is given by pi square A by LE square. If anybody asks you, what is critical load of column? Your answer should be like this, man. Pi square A by LE square. Don't say L square. This formula is valid for any kind of end conditions. Either both ends fixed, both ends pin jointed, any type of end conditions. Even any mode also, with any number of stops also. Okay? So for all kinds of columns, this formula we can use. This is universal formula. For all columns we can use it. Please write it, man. P is equal to Euler's critical load of any column with any end conditions, with any mode, with any number of stops is given by this. Write down, man. Euler's critical load of column. Euler's critical load of column. Euler's critical load of column with any end conditions. With any end conditions. With any mode shape. With any mode shape. With any number of stops. With any number of stops. With any number of stops is given by P is equal to pi square A by LE square. So P is equal to pi square A by LE square. Here LE is effective length. Here LE is equal to effective length. Okay, so we discussed critical load. We discussed what is effective length. Sometimes in examples, sometimes in gate questions, they may ask you like this, man. Indirectly, they ask you about critical load. A column they will give, and simply they will ask how much minimum load should be applied to induce permanent buckling in the column. How much minimum axial compressive load should I apply to induce some permanent buckling? So like that they may ask you. What is the load, man? That load is nothing but critical load. Critical load is the lowest axial compressive load which may induce some permanent buckling in the column. Okay? So like that you have to understand. So in next session, we are going to discuss critical load and effective length of various end conditions with various modes and some special cases, man. We discussed 4 standard end conditions. Apart from these 4, 3-4 other end conditions are there. So in coming session, I am going to discuss the other special conditions also for the sake of civil engineering students. So until next session, have a good day. Thank you very much.